Everybody to this session at the 2023 OFA virtual workshop. In this session today, we'll be covering an introduction to Compute Express Link 3.0. We'll go through sort of a recap of CXL 1.1 all the way till 3.0, and we want to highlight all of the capabilities that we're bringing with CXL 3.0 that's really useful in expanding sort of fabric capabilities and the management interfaces that go along with that. So for those who are new to Compute Express Link, this is an industry open standard for high-speed communications. You can see here the CXL board of directors across a widespread of companies. And then from a membership perspective, CXL Consortium is going very strong with more than 240 plus member companies. So it was established in 2019 with the specs being available and on a steady cadence of specification deliveries through the years. Right. So just a quick overview of what CXL is. It's bringing really a new breakthrough high-speed fabric capabilities. Fundamentally, it starts with having and leveraging a high-speed interconnect between CPU, memory, and accelerators. It builds upon what is available on PCI Express as an infrastructure. And what I mean by that is its premise is leveraging PCI physical and electrical interfaces so you can get all the goodness of development that happens on PCI Express, and then add on top of that some essential key protocols that are required for these new use models. And what we mean by that is bringing memory coherency semantics and memory semantics for CXL attached devices. And the key benefits that you get by enabling that is now you can enable fine-grained resource sharing so that you can address some of the high performance requirements for heterogeneous compute environments. So this would be either you're bringing accelerators or you're bringing cache semantics to the accelerators so that you can improve the performance for those devices. A big factor of any of the data center or high performance solutions is really memory. And as we all know, the memory costs are increasing. Memory is a significant portion of any solution that gets deployed. And with CXL, we're bringing a lot of flexibility and capabilities onto a memory hierarchy and memory architecture. So it enables use models such as memory disaggregation. So you can have memory in sort of a pool. It's extending the semantics to then sharing the memory. And we'll talk a little bit more as we get into the details about what are the distinctions of pooling and sharing and how do we bring that up. But the key point to notice there would be that your memory as a resource, now you can effectively manage it across many different nodes, right? So that's sort of the value proposition for that. Another key aspect is bringing persistent memory semantics. There are a lot of use cases that are dependent on having a memory, but providing persistent characteristics for that memory. So CXL brings those capabilities. And finally, addressing the emerging memory media. So CXL abstracts the memory interface and then enables different memory media to be connected behind CXL and bring new and interesting use cases to the market. So really addressing both the coherency requirements and the memory requirements and really delivering it as an open industry standard and bringing all the players that are the compute vendors, the memory vendors, the system vendors all together to address those requirements. So as a result of that, CXL has established as an industry open standard for coherency protocols as well as memory protocols. A key aspect of our development and our philosophy has always been as we develop the CXL 3.0 specifications or any of the CXL specifications, we want to make sure that it is fully backwards compatible with CXL 1.1 and CXL 2.0 as an example. And the key reason for that is all of the investments that people make into the technology, you want to make sure that you can recoup your investments in it. And you always have a capability for devices to be, to plug and play in, future generation of products as well. So a lot of emphasis is put in by the consortium and the technical work groups as we develop these technologies to keep backwards compatibility right in the center of all of our developments. And as you will look into it, all of our development for CXL has been really incremental. We've been looking at all of the use cases, identifying which ones are the ones that we want to address in the generations of specification, and then put a cadence for how these technologies come up. And that will continue to grow. So we're looking at having a continuous innovation in the pipeline and bringing those things through different versions of the specification. So just to put that in highlight, the CXL specification release timeline, March 2019, CXL 1.0 specification was released with the objective of direct attach accelerators and memory devices. As we get into the second generation, consortium incorporated that CXL 1.1 specification was released. And then, approximately a year later, CXL 2.0 specification was released, extending the scale with, adding new capabilities, introducing pooling, concepts of switching and pooling in CXL 2.0. And then in August 22, CXL 3.0 specification was released, now adding more capabilities, adding scale-up properties to CXL 2.0. And we'll go and cover some of those details. Quick recap of what CXL is between CXL 1.0 and CXL 1.1 usages. So we define the devices that attach to CXL, we categorize them into three different types, type 1, type 2, and type 3. Essentially what CXL is bringing three different protocols, CXL.io, CXL.cache, and CXL.memory on a common interface, making use of a PCI Express physical layer as the underlying infrastructure. The key distinction the key capabilities that we bring with CXL is the ability to interleave between CXL.io and CXL.cache at a fine grained granularity. That way we can address the performance characteristics. And then the other key aspect is that latency is in the center of all of our development. So we continue to look at keeping node level properties for these protocols. So the three protocols that we define are CXL.io, which behaves and functions exactly like PCI Express. And then CXL.cache is extending the cache semantics to an accelerator. And then .memory is extending the memory semantics to over the interconnect to an accelerator or a memory controller. So the first one is a type 1 device. This is a device, an example of that would be an accelerator that can take advantage by adding caching properties to that accelerator. So think about if you have cores on the processor, you improve the performance of the cores by having cache coherency semantics, and as a result of that, you can you can implement much efficient sharing between the different cores on the processor. If you think about an accelerator as an extension of a core, then you can provide with caching, you can provide the same capabilities over to an accelerator. The accelerator just happens to be behind an external link, right? So .cache brings that capabilities to the .cache protocol brings the capabilities to an accelerator, where now the accelerator can cache CPU attached memory similar to the way a CPU processor can cache, memory attached to DDR. And it is defined in a way which keeps the cache coherency semantics simpler to implement from an accelerator's perspective. And that was the whole, motivation behind that. So a type 1 device, for example, would be an accelerator device that has caching semantics, and that's the only protocol that it supports. Now, keep in mind that CXL.io is a common protocol across all the three use cases, and it's required for device discovery and as such, right? And then if you're just supporting .cache, that makes you a type 1 device. The advantages that you have with such a device, such an implementation is you can implement better atomics because you can bring a cache line into the accelerator and then you can operate on it. So that's some of the advantages you can get for a type 1 device. Type 2 device is an accelerator that has local memory attached. And in that case, you want to have the ability to map that local attached accelerator memory as part of the overall system memory. And then in addition to that, you also support the .cache protocol. Now it's providing the capabilities for that accelerator to cache local memory and CPU attached memory. And it's also extending the capabilities for the processor to cache local memory as well as the accelerator attached memory. And a good example of such an accelerator would be, GPGPU type of devices, a dense computation where you're operating on a larger data set. You want that data set to be closer to that accelerator so that you're working on that data set, and then the results of that is something that you're sharing with the processor. So it's very useful for those type of use cases, and the dot cache and dot mem protocol enable to build such an accelerator and then address some of the requirements. And then the last device type is type 3. This would be memory buffers. So in this case, you're utilizing the CXL.io and CXL.mem memory protocols. And think about it as you're extending the memory controller out of the processor over onto a device, and you abstract that interface so that you can attach any memory media type behind that device. And you do that by providing the memory semantics over CXL. Now, the use cases that it enables is memory bandwidth expansion and memory capacity expansion, and in many cases, both. So you can think about adding more capacity to the system, adding more memory bandwidth to the system by adding these memory controller devices. The interface is abstract, so the memory media type could be DDR4, DDR5, it could be storage class memory behind it. And then the additional use cases that you bring along with this is also the media type could be persistent memory. And you can bring in persistent memory through many different types of media devices. And it provides the flexibility to the memory controller devices to differentiate and bring new memory capabilities. So that type of a device where you're extending memory only capabilities is what we categorize as type 3. So that was sort of the early definition, making sure that we define these devices as type 1, type 2, type 3. They're direct attached to the on the link, and it is what we call CXL 1.0 and CXL 1.1. With CXL 2.0, we extend the capability now to provide more scale. So you can think about a few things. We can extend it as a fan out. So for example, with CXL 1.1, these devices were direct attached to the host. Now you can extend the capability by a switch to increase your fan out, as shown in this example, for more than 4 devices as an example. So now it provides you the capability to have a memory expansion and extend your capabilities in terms of just the capacity that you can add behind, and now utilize a CXL switch to do that. One additional thing that CXL 2.0 did was in CXL 1.1, all of the devices were visible as root complex integrated endpoints. With CXL 2.0, the CXL devices are now visible as PCI Express endpoint devices. And we can start making use of some of the hot plug capabilities that you get with PCI Express. We can now leverage that with CXL 2.0. So along with switching, it's also extending the capability from a device discovery perspective that you can make use of PCI Express device discovery mechanisms, right? And then the other interesting use case from a memory disaggregation perspective and effective memory resource utilization perspective is the concept of CXL 2.0 memory pooling. And what we mean by that is you can take memory as a resource, you can partition that resource into multiple different partitions, and then allocate that a given partition to a given host. So in this example, we're showing multiple different hosts. They're all denoted by H1, H2, H3. The different colors represent sort of a host domain. And then you have devices D1, D2, D3, D4 as shown in this example. And then a device can partition its resources and then allocate those resources to a given host. So if you follow the colors, like a D1 device, it's completely allocated to the host 1. You can look at device D2. Some portion of its memory is allocated to host 1, and some portion of it is allocated to host 3. So these concepts of identifying a device and identifying the capabilities of those devices, partitioning the memory resources within those devices, and then assigning them to the host is all that is defined in the CXL 2.0 specification. Such a device that you can share or you can pool across multiple hosts is called a multi-logical device, because when this device is configured, it's then configured into logical devices, and then you assign a logical device to a given host. So that's how um, the allocation and the mapping happens. One of the key things that CXL 2.0 added on top of what was available in CXL 1.1 was a persistent flows, which is if the media type is persistent memory, then you want to, for impending power failure notification, power failure events, you want to provide the capability where you can send notification messages to the devices. So with CXL 2.0, there are semantics that are added that allow a system to then notify of an impending power failure system-wide, and there are flows that are defined for how memory persistency can be guaranteed, which includes coordinated flows for flushing system level caches and making sure that the data is persistent. So all of that, those flows were covered in CXL 2.0. And as I talked about, the pooling of accelerators, the management for how these devices are discovered, how these devices are configured, that is done with pooling of accelerators and using a fabric manager concept. And there are APIs that are defined for the device discovery and the pooling of those devices.
It might be appropriate at this point. There's a question.
Sure.
Is the event information available in the CXL 2.0 data sheets?
The event information in terms of the node, yes, it's part of the switching chapter, as well as the command interfaces. That's where all of these APIs and the commands are defined in terms of how you discover the device, how you coordinate and configure the device, if that was the question. And the objective behind that was to keep it media sort of agnostic, so you can come through in-band or out-of-band mechanisms to configure and program the devices. Because it's defined at an API level, it allows you to do that.
Cool, thank you.
Right. So we'll go with the motivation for CXL 3.0 specification. So with the work ongoing at around CXL 2.0, we were also keeping an eye on what the industry trends are and what are the requirements, right? So one of the key things was, from a use case perspective, you're looking at needing more bandwidth. Either you're looking at more system memory bandwidth, you're looking at accelerators or SmartNICs, looking at PCI Express Gen 6, and making sure that we scale up to provide the bandwidth requirements for that, right? So one of the industry trends we were looking at is the need to get to higher bandwidths. And either it's accelerator devices or it's for requiring more memory capacity and bandwidth per core, right? So you're looking at how do we get more scaling in terms of memory capacity, and then just how do you achieve more bandwidth per core? And you can look at from a bandwidth perspective, you're looking at how do we just increase the interconnect bandwidth, right? So that was one of the industry trends. We were looking at use cases. Once pooling was established, there were a lot of interest coming in for use cases that are interested in sharing. And it would be good to introduce the concept of sharing at this point, which is the one I talked about. Pooling is when you take a memory resource, you partition the resource, and then the partition is assigned to one host, right? And in which case you're not every host gets a dedicated memory resource for its use. What sharing describes is to take that resource and map that resource in both the host domains so that they can physically share that given resource. And there are several use cases that were coming in light to enable those. So we had to look across that. There were important semantics such as messaging across those domains need to be addressed. How do you effectively share such a device? And finally, the one that was looking at is memory bottlenecks due to CPU pin and thermal constraints. So there was things required to look at where memory technology is going and how can CXL help and augment some of that so that we can address the memory bottlenecks. So several things were added to the CXL 3.0 specification to address that, right? So in terms of doubling the bandwidth, we moved to CX, PCI Express Gen 6, right? Data rates, and now that allows you to double the bandwidth. The key important part about it was to make sure that we get there without adding any latency. So a significant amount of work was done in there to make sure that we get to doubling the bandwidth with a zero latency adder over CXL 2.0. So that's significant, and it goes back to our emphasis on continuing to maintain node level properties as we continue to evolve the CXL specification. As we look at the fabric capabilities, we had to define one of the use cases that we talked about CXL 2.0 was you can get to device sharing and memory pooling using a switch, for example. But there were a lot of use cases that you could get to sort of a pooling capability by just having a multi-headed device. And what we mean by multi-headed is a memory controller that has more than one port. Right? So the feedback was to incorporate such use cases and define them in the CXL specification. So the multi-headed aspects were added. As we get into sharing, you now have to think about the fabric attach as we're scaling up. So the concept of fabric attached devices, which are enabling sharing of memory, was added. Enhanced fabric management was added to CXL 3.0. And then the whole idea of having a composable disaggregated infrastructure and all of the management support to enable that was added in the CXL 3.0 specification. Now, in terms of the capabilities that come along with the scalability and for addressing the resource utilization is now you can build enhanced memory pooling. So a good example of that is dynamic capacity devices is a feature that is added. So that describes the capabilities to when you're onlining and offlining memory. Now you can make use of those capabilities so that you can build an enhanced memory pooling solution. CXL 2.0 defined single level switching. With CXL 3.0, it describes multi-level switching. Concepts were added for peer-to-peer accesses by devices, and some new memory, symmetric memory capabilities were added, and we'll talk more about that. And overall, improved software capabilities to manage these devices and these features were added. And the key thing that I talked about before was continue to maintain full backwards compatibility with CXL 2.0 and 1.1 specifications. So overall, CXL 3.0 is a huge step function in terms of bringing fabric capabilities while maintaining backwards compatibility with prior generations. So a quick touch on, how do we get to CXL 3.0? So we get there by, doubling the bandwidth, but keeping the same latency. So with CXL 3.0, you make use of CXL 6.05, so you can deliver, at 64 giga transfers per second data rate, use PAM4, and leverage all of the PCI goodness. From a FLIT perspective, CXL defines basically, a 256 byte standard FLIT layout. And in addition to that, it also provides the ability for a 256 byte latency optimized FLIT layout. And this is really key because now it allows you to build a solution without having any latency adder, right? And the details are all listed here. And the capability extends to support this overload lower data rates as well. So you continue to operate in this new FLIT format at 8 gig, 16 gig, and 32 gig data rates as well. Now, the key thing happens as we look at this new standard FLIT format is it enables, from a protocol perspective, new enhancements that you can add, and for the protocol FLITs that in the previous generations, when you look at the 64 byte FLITs, you were running out of space in terms of adding more capabilities. So with a new FLIT format, it provides you the capabilities to add more add more protocol enhancements because you have a little bit more headroom now for those things, right? So here's, a PCI 6.0 FLIT is shown, and then, what we're showing here is the distinction between that and the 256 byte FLIT format that you have for CXL, and then the two were the latency optimized FLIT format. We'll cover it from a protocol enhancements perspective. We look at CXL 3.0 from a protocol enhancement perspective. One of the key features that was added was the ability for CXL 3.0 to enable non-tree topologies and enable peer-to-peer communication. And as an example of that, a peer-to-peer communication was a use case where you have, any one of those devices as an example, this D1 device having a capability to directly access the what we call HDM memory. So any memory that gets mapped in CXL is defined as an HDM memory. So having the capability for direct peer-to-peer access for that device to access any of the HDM memory is what was added to the CXL 3.0. Prior to this, anytime you had to access a peer memory, you had to bounce off the host processor through the host processor's cache coherency semantics, and then down over the CXL devices. Now, this provides you an efficient path to directly access at the switch level between any of the two devices, right? And you achieve that through the peer-to-peer mechanisms, and to enable that, a new unordered I/O flow was defined in CXL 2.0. This is taking advantage of the UIO definition that is defined and driven through PCI Express. We make use of that in CXL.io to now define, this unordered I/O semantics that would allows you to access any of the CXL devices. Now, from a coherency perspective, when you provide this direct peer-to-peer access, you need an ability for that device to then make sure that it's keeping the data coherent with the host domain. And to support that, there's a new back invalidation that is supported on CXL.mem. So think about what that is enabling is, the devices that have HDM memory to now build a Snoop filter and keep track of the lines. And to enable that, there is a back invalidation protocol that is supported that allows for the device to then manage the coherency, right? So those were the extensions. A new channel was added to CXL.mem in the CXL 3.0 protocol, and that allows these new use cases for peer-to-peer connectivity. Just to give you an example, right, is this mapping. For example, if you have a large memory in a type 2 device, then from a scaling perspective, it was deemed that we need to extend it and support the capability for adding, for the device coherence mechanism that's there on the device, to extend it to add a Snoop filter type of capability. And as an example that's shown here, and the one that I was talking about, when a host makes an access to the device coherence space, when there is a miss, you send a back invalidate from the device coherent agent. So you send that back invalidate to the host, you snoop the peer cache, you get the data that was modified, send the data back to the device, and then the device then will update its memory with the new and updated content, and then the host that was asking for that data gets the data back from the device. So it's now extending this semantics for the device to implement a Snoop filter and then participate in cache coherency semantics directly with the host. And in terms of CXL 3.0 memory pooling and sharing, so with CXL 3.0, we extend the capability now for sharing of a device, sharing of CXL memory. And in that case, what it means is that that same physical memory is now mapped across multiple different domains, and you can share that same physical memory across the domains. So an example of that would be the memory that is S1. So you can see that multiple hosts have that particular S1 copy. Is host 1 and host 3 as an example have that same memory line shared across them. And that's bringing in some very interesting use cases. If you have to provide a fully cache coherent memories system across these hosts, then you have to have the ability for such devices to support a directory and a back invalidate mechanism. And that's what the CXL 3.0 protocol extends. And such a device that you can share across multiple hosts, we call we categorize such a memory device as a globally fabric attached memory, and there are semantics that are defined in CXL 3.0 for how to map that memory and access it. And finally, CXL 3.0 extends for multi-level switching. With CXL 2.0, multi-level switchings you could enable it, but it was left into implementations to do that. And with CXL 3.0, we extend the capability for both, for extending that now to support multiple levels of switches, right? And then the other key thing that we bring from a scaling perspective is that with 2.0, you can attach only, and in a given hierarchy, you can only connect one CXL.cache device. CXL 3.0 extends that capability for, CXL.cache devices to be extended up to 16 CXL.cache devices per root port. So it's adding the scale up for accelerators as well. So what is this enabling? If you look at as an example, it's bringing in the composable systems that you can implement as shown in this example, leaf and spine switches. And it would allow you to build a composable system where you have CXL switches. You can have a domain of CXL switches where you have global fabric attached memory. You can have a pool of CXL switch with NIC devices, accelerator devices, or a combination of both. Right? So it's enabling systems to be built that provides a composable architecture, right? And with CXL 3.0 capabilities we're bringing in. So I know I'm running out of time. I'm 1 minute over. So in closing, right, with CXL 3.0, we bring full fabric capabilities. We extend the switching topology. We bring rich coherency capabilities to CXL 3.0. Peer-to-peer now becomes the center of the capabilities that we bring in. We double the bandwidth, keeping no impact to latency, and continue to maintain full backwards compatibility. We're enabling several different use cases. Our call to action is download the CXL 3.0 specification. If you are interested in it, want to contribute to it, you're always welcome and encouraged to join the consortium. And if you want to know more about the details, you should, and news coming from the consortium, follow us on Twitter and LinkedIn for updates. Thank you all. That's all I had. I know we are short on time. One of the things that we talked about, if there are more questions, we will look into those and submit them, but maybe we could take a couple of questions if we have.
Yeah, absolutely. If someone has some questions, please speak up or type it into the chat, and we're happy to take a couple of questions. Okay, I do not see any questions on the chat. Last call for questions right now or you can of course go to the talk to Mahesh or the CXL Consortium yourselves. Okay. Oh, wait, here's one from Mr. Doug. Any idea on general hardware availability?
Yeah, I mean, generally from a consortium perspective, we don't talk about product availability, but if you are following a lot of news around what's happening in the ecosystem, there is, with CXL 1.1 and, 1.0, there are, hardwares, that is available in the ecosystem. So the ecosystem traction is going pretty good and expected to the way we would see a new technology evolve. And in fact, from what we've seen for a first generation of a technology, we're seeing pretty good adoption in the ecosystem for this. So 2023-24, we expect to see all of these, the early capabilities start to show up in the ecosystem.
Cool. Thank you. Okay, thank you, Mahesh.
All right. Thank you all. Thanks for your time.